Welcome to Algebra 2, Chapter 9, Section 1. We're going to be talking about sequences and eventually series in this chapter. So first of all, we have some notation to learn about. We're going to talk about the nth term of a sequence and how to write different rules for sequences. A little bit of vocabulary and some interesting sequences. In 1202, Italian mathematician Leonardo Fibonacci described how fast rabbits breed under ideal circumstances. He noted the number of pairs of rabbits each month formed a famous pattern called the Fibonacci sequence. We will be talking about that one in particular more later, but for now, we're just going to start with some basic sequence terms. A sequence is just a set of numbers. You've probably been doing these since elementary school. 1, 2, 3, 4, what comes next? That is a sequence. So each term of the sequence, we'll number those. Term 1, term 2, term 3, term 4. Some sequences are infinite. They go on forever and they'll have like a ... ellipsis at the end. Some are finite and they stop. Like here's an example of a finite one, 1, 2, 3, 4. You can think of a sequence as a function by thinking of the term number as the domain. So if I have term 1, 2, 3, 4, those are the natural numbers. That's why this says natural numbers here. And that can be my input, my x, my domain. And then the actual sequence itself is the range or the output. The term numbers are usually represented by n instead of x. We could still use x, but we use whatever letter. So they use n for the term number. The first term would be a1, a2, a3, a4 would be each term. So we can have n number of terms, which is a sub n. And that's how you say it. You say a sub n. That's a subscript notation. So here is a sequence in a table here. So n is the term number. So this is term 1, 2, 3, 4, and 5. an, so this is term a1, a2, a3, a4, and a5. So this is your n, this is your an. This is the beginning of Fibonacci sequence. So it always starts out with 1, 1, 2, 3, 5. And if you can figure out the pattern there, you can pause the video, try to figure it out, or you can read down below because here we go. It says the first two terms are 1, and each term after that is the sum of the two terms before it. So if I take 1 plus 1, I get 2. If I take 1 plus 2, I get 3. 2 plus 3 is 5. 3 plus 5 is 8. And so I can finish going on down the sequence. This is a recursive formula for the sequence. Basically, to find whatever term I want, I need to take the two terms before it. And this is a notation thing that gets a lot of people hung up right here. This is my whatever term I'm looking for. So if I back up one term, that would be the term before it. And if I back up two terms, that would be two terms before it. It does not mean I'm taking that number and subtracting 2. It means I'm moving backwards 2 terms, 2 spaces before. So when you have a subscript, it's your location. It's not math that you're subtracting 2. So if I was looking for term a sub 6, which is this one right here, I would need to take a sub 4 plus a sub 6 minus 1 is 5. So I would take the fourth and the fifth terms and add those up. There's an a there. A sub 4 plus a sub 5. So a sub 6 is 3 plus 5, which is 8. So that's like notation-wise what I'm actually doing here. All right, so here's some examples of what the types of problems that you'll have will look like. They're not all going to be Fibonacci. They're just going to be sequences made up by a different rule here. So find the first 5 terms of the sequence with a1 equal to -2. Well, guess what? They just told you a1. You just did 1/5 of the problem without doing anything. Now, to find the rest of the terms, here's my rule. So I'm going to use this rule, this recursive rule, because it has this n-1 thing in it, to find them. So for the second term, I want to find a sub 2, and the n has to be bigger than 2 because we're starting with the first term. So a sub 2, I would need to take 3 times, and if I plug a 2 in here, this would be a sub 1. Well, I already know a sub 1 is negative 2. So the answer to that is negative 6 plus 2 is negative 4. And that's how you find each of these. So to find a sub 3, I'm going to take 3 times. Well, if I put a 3 in here, this is a sub 2. So I need to take the second term. I'm not subtracting 2 from it. I'm taking that term before. So this a sub n minus 1 means the term before. So I take what I had, negative 4, plug it in there. 3 times negative 4 is negative 12, plus 2 is negative 10. And you can keep going. So you don't have to write this out every time. 3 times the term before. Let's just plug it in there. Negative 30 plus 2 is negative 28. And then to do one more, a sub 5, we would do 3 times negative 28, the term before, and then add 2, which is negative 82. So this is called a recursive formula, and it relies on the term before. So let's try another one of these. There we go. I'm going to have you pause the video, try that out, and then you can check your answers here. We already know the first term is negative 5, so plug that. That's one answer. And then you plug that in. This a sub n minus 1 is where you're going to replace the previous term. Pause the video, answer all those. All right, so that very first one was given to us. There's no math to do, and you don't have to write it like this. They just showed this. When I plug a negative 5 in here, I'll do negative 5 minus 8, which is negative 13, and then I do negative 13 minus 8. So these are the 5 answers you should have gotten on that problem. Here's another one. This time we have a sub 1 is 2, and then this one is multiplication. I'm going to do negative 3 times my previous term. So pause the video, put those down for the first 5 terms. See if you can do it. Welcome back. Here are the answers where we're given the first value, and each of these are times negative 3. So we're just basically finding the pattern here is that we're just multiplying every time times negative 3. There's one more. This one is not a recursive. So notice this equation is different. This is what I want to point out. This is not a recursive equation. Why is it not recursive? There's no a over here. Okay, a sub n means the term number. N is the number. The a sub n is the value of the term. Sorry, n is the number. So if I want to find the first term, well, guess what? They didn't give me the first term. But the first term is a sub 1, right? That's when n equals 1. So if n is 1, I just have to put a 1 in there. And if a is 2, I have to put a 2 in there because that's just n. It's not the previous term this time. It is the term number that I'm looking for. So all I have to do is plug it in. So to finish this problem, just type these in your calculator or whatever, and we would have our first 5 terms. Hopefully they're right here. Oh, that didn't work. Hold on. There we go. So they're not quite lined up, but that's the first term. So 3 minus 1 is 2, 9 minus 1 is 8, 27 minus 1, and so forth. So there's your answers. So this is a general form. It's not recursive. General form of a sequence. Same one here. There is no a on this side, so it doesn't rely on a previous term. It's called an explicit form or just the regular form of a sequence. So try this one out. Plug in a 1. See what you get. Find the first 5 terms. Pause the video. Come on back. All right, here are the answers over here. 1, 2, 3, 4, 5. First 5 terms. And you can also put these in a calculator. If it has the a sub n, you can't really put that in your calculator, but this one you can put it in and just call this x. So x squared minus 2x would go in your calculator, and then you can graph it. You can look at your table of values. If you look at your table, you can see all these same terms of your sequence. You can also see a visual if you graph it. All right, so what I said is this is called the explicit form. This defines the function as a function of n. So it does not rely on the previous term. It just needs to know the nth term. Why this is I like the explicit formula better is because if I want to find the 10th term, I plug in a 10 and I'm done. If I have a recursive formula and I want to find the 10th term, I have to find the 9th and the 8th and the 7th and 6th all the way on back. So it can be really tedious if you want to find like the 100th term. Just a reminder from previous lessons this year, linear patterns have a constant difference. So if it's going up by the same amount over and over and over again, then you're going to get this a line because it's basically creating your slope. Quadratic patterns have a constant second difference. So if you did the difference and then you did the difference again and they were all the same, you'd have a quadratic. And exponentials have a constant ratio. So if you're multiplying by 2, by 2, by 2, by 2, that is exponential to the power of 2. 2 to the power of something. So let's see if we can write an explicit rule for some of these sequences. So let's start out here. We have 5, 10, 20, 40, 80. So first thing you want to do is figure out what's going on here. So are we adding 5, adding 5, adding 5? No. Are we multiplying by something? Let's try multiplying. If we multiply by 2, multiply by 2, multiply by 2, multiply by 2, that works. So this one has a common ratio. So because it has a ratio, we know we're going to have an exponential. So that helps knowing those things. If it's adding, you're going to have linear. So let's try this out. We know the first term is 5. How did we get the second term? Well, we took 5 times 2, right? I'm just going to kind of like write out and see if I can come up with a rule for the nth term. To get the third term, I took my 5 times 2 and I times it by 2 again. So notice what's happening here. Fourth term, 5 times 2 times 2 times 2. So let's see if I can shorten this. For the fifth term, how many 2's did I have? For the fourth term, I had 3 2's. So for the fifth term, I have 4 2's. So instead of writing it out, I'm going to write it with an exponent there. So notice, since I had a starting value, I have 1 less 2 than I have for my term number. So let's see if we can jump down here. Let's just say, what if I was looking for the 10th term? How many 2's would I have there? Well, we decided that it's 1 less than the term number. So this is a 10, this will be a 9. Okay, now the whole point of this is to write an explicit rule for the nth term. So the answer to the problem is what I get for the a sub n equals. And well, these all start with a 5, so I'm going to start with a 5, which is my first term. And then I'm all multiplying by 2, but what power is going to go here? So remember, it was 1 less than whatever this was. So it's 2 to the n minus 1 power. And you can put that in parentheses or not. It doesn't really matter. But this is called the explicit rule for this function. I can kind of create it by seeing what pattern is happening. Let's take a look at another one of these and see what happens here. So first of all, let's examine the pattern. Do you see a pattern between these? They don't look like they're going up super fast, so I'm going to try subtracting and see if I can find the common difference. So when you subtract, take the second one minus the first, so that's adding 2.5. That's adding 2.5. Yep, looks like we've got a common difference of 2.5 because I can just subtract these. That means we're going to be linear, right? So if we have a constant difference, it's going to be linear. If we have a constant ratio, like on the last problem, it's going to be exponential. All right, let's write our pattern. The first term is 1.5. To get the second term, we took 1.5 plus 2.5. To find the third term, we took what we had, 1.5 plus 2.5, and then we add another 2.5. Let's shorten that. For the fourth term, 1.5 plus. How many 2.5s are we going to have? Again, we have 4. The fourth term, 1, 2, 3, 4. To get here, how many 2.5s did I add? I only added 3 of, oh, that doesn't go there. I added 3 of them, 3 times 2.5. So we're going to go ahead and jump to the rule now. I'm going to start at 1.5 because that's my starting term always. And I'm going to add, I kind of wrote this backwards, but my constant difference was 2.5. And I'm going to multiply that by how many of them I'm going to have, which is always 1 less than n. So here's my explicit rule for a linear sequence. And for this chapter, I'm going to give you a sheet of formulas, and this sheet's basically got this formula on here. A sub n is 1.5 plus, oh, sorry, we're doing it not 1.5. The first term, 1.5 was the first term, right? So we take the first term. What was the 2.5? That was our common difference. And then times n minus 1. So this is really just a little simple formula you can always use to build these. You don't have to do all of these steps every single time. How about this one? Can we write an explicit rule for this one? We've got 1, 1/2, 1/3, 1/4, 1/5. Well, I don't think that's adding the same amount every time. Because if you add fractions, you know, you got to get a common denominator, all that stuff. It's not multiplying the same time, but can I relate the x values or the n values of 1, 2, 3, 4, 5 to this sequence? Do you see any connection here? Is my a sub n related to my n? I think we can come up with a really easy rule here. We could just do 1 over n. If I wanted the 10th term, I'm pretty sure it'd be 1/10. If I wanted the 100th term, it'd be 1/100th. So just by putting 1 over n, we can come up with that rule. So it doesn't have to be, have a common difference or a common ratio. It can just be another way to write the pattern. Here's another example. We've got a ball. We're basically dropping a ball, and it's bouncing to 70% of however high it was the bounce before. And we're going to get something like that. We're just going to graph the height of the bounce, and it says the bounce is to a height of 4 feet. So my first bounce is at 4 feet. So I can graph that. First bounce, 4 feet. And I'll show you on the next page in a second. Each time after that, it's 70%. So if I did 4 times 0.7, I would get 2.8. So that at my second bounce, it's going to be at 2.8 and so forth. So let's graph this. We're going to look for the value and the 10th bounce. Now I could just keep multiplying by 0.7, 0.7, but we're going to write it out as a sequence and graph that. So here's a graph of what they look like. So you can see that if we had these be our x's and these be our y's, we can actually get a graph here. We are multiplying by 0.7. So 0.7 times, wait. We started at 4 and we're multiplying by 0.7. This should be times the previous one. Whatever the previous one was times 8/7. So this is a recursive formula, whatever I had times 0.7. I could also come up with an explicit rule. My explicit rule would be I would take 4 times 0.7 to the, well, if I'm looking for the 10th term, how many would I do? 1 less, because I already started at the first. I have to do 9 of them. So for the 10th term, a sub 10, I would do 4 times 0.7 to the 9th power. And that should be the answer for the 10th term. And I believe that is shown right here. Well, they're coming up with a pattern, which we already did. So here's my final answer, 0.161 feet. And obviously, with physics, eventually it's going to be such a small bounce that it's not really going to be bouncing anymore. So here's just another example. If you want to, you can look at this, but basically a toilet, every time you flush it, is 1.6 gallons. So how much total water is used? That's going to be linear because every time you flush, you get another 1.6. All right, the last part of this lesson is on iterations. So if you have seen fractals before, they can make very beautiful images by repeating a shape and pattern and sometimes rotating it or moving it around. It's basically repetitive application of the same rule over and over again. This example here is called Sierpinski's triangle. Basically, you start out with one triangle, and then you draw or cut it into 3 more triangles. So by drawing these 3 lines, it actually makes 4, but you just draw a triangle inside. And then the next one, any of these blanks. So now you have these 3 triangles. And then out of those 3, I know what it is. You're cutting out the center. So you cut out the center triangle, and that leaves you with 3 triangles. Then the 3 triangles that are here, you cut out the center of those. When you remove the center, keep pushing this little button. So let me color in. This is what you're left with. You have one full sheet, you cut out the center. Then when you cut out the center of each of those, you're left with how many triangles are here? 9, because I just counted them. And then each of those we cut out and cut out and cut out. And this is called Sierpinski's triangle. And what they want to know is the number of triangles in the 7th and 8th iteration. So iteration just means like the 7th or 8th term. So for this is my first term, my second term, my third term, my fourth term, and I want to find the 7th and 8th. So let's see if we can find a rule first. What am I doing? By cutting out the center of each triangle that I had is creating 3 new triangles. So my first term is a 1, my second term is a 3. What is happening here? I'm multiplying by 3. So I'm going to multiply by 3 every single time. To get the next one, I would take 3 times 3. To get the next one, I would take 3 times 3 times 3. So I can actually shorten this really quickly. The nth term would be 3. How many 3s do I have? Well, for the fourth term, I have 3 of them. So that's 1 less. 3 to the n minus 1 power. So my question asked me for the 7th and 8th iterations. So I would do 3 to the 7 minus 1 and 3 to the 8 minus 1 power. So these are going to be the answers to how many triangles you would end up with. 729 and 2,187 are the answers for the 7th and 8th iteration. One more question. This one is the Cantor set, which is remove. It's a very similar idea. We just have a line and we're removing the center third. So we take this line, cut it in thirds, and take out the center. Then we take each of those lines, cut out the center third. So the first iteration has 1 line, the second has 2, the third has 4, and then those are each going to have the middle removed, so there's going to be 8, and so forth. So how many are in the next 2 iterations? Well, we just did that one. So basically, it's doubling every time. So a sub 3 is 8, and a sub 4, 4 is 8, and 5 is 12. 1, 2, 3, 4, 5. And that concludes lesson 9-1.